Well, good evening, ladies and gentlemen. We're going to be talking about 9.2, which is conservation of momentum. Conservation of momentum deals with anytime you have a collision or a separation. So meaning if anything ever collides with something, like a large truck here colliding with a car, here you've got a ball being thrown at a girl on roller skates, or a separation, firing a gun. And I found a couple of really interesting videos that deal with collisions. First of all, here's a young man who learns the hard way how not to play paintball. Watch it again. We've got some pretty good separations here. Let's see here. Let's see. Yeah, here we go. So this guy straps a bunch of 2-liter water bottle rockets to his back to see how well they work. So this is separation. You've got water being ejected backwards, which forces him forwards. I found an interesting video of an astronaut talking about conservation of momentum from the International Space Station. I thought we'd watch it.
Momentum tells us that the total momentum in any closed system will remain the same all the time. And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving and causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So for example, if this had a velocity of 0, and that had a velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same. So for example, if I can get these two to stick together, while one is stationary and the other is moving towards it, once they stick together, the total momentum will remain the same, so the combined objects will have half the velocity of the one initially that was moving. Conservation of momentum makes it actually quite interesting and challenging to move around the ISS if you don't have something to reach onto a handhold. Because if you get trapped out in the middle, there's no wiggling you can do, no swimming you can do that will get you over to a handhold so that you can pull yourself to move through the station. Because no matter what I do here, if I just stay floating in the middle, I'm just going to remain here in the middle since the total conservation, since the total momentum of the system has to remain constant.
So what he's saying is really important. Thing number one is that the momentum before any collision will always equal the momentum after any collision. Now that's only true if two things, that if there's no forces interacting, like you have no exterior force, or you don't lose any or gain any mass. So they call that a closed, isolated system. So let's take a look here. this is a closed system. We call this an isolated system. So if that's true, before the collision, the momentum will always equal after the collision. So I've got a couple of examples here. Here's our first example. There's a car that's going 25 meters per second, and it's 1875 kilograms. It rear ends a very small compact car. That's stationary. No, it's going 17 meters per second. They stick together. And they move off together at a certain speed. What is that speed? So that's what he was talking about before when he had the tennis balls with a with the Velcro. They're going and they stick together. So the momentum before the collision, assuming that there's no outside forces interacting and we're not losing any mass, that the momentum before the collision is going to equal the momentum after. Now the momentum, there's two different objects that have momentum. There's the momentum of the big car and the momentum of the small car before, and then afterwards it's them together. So we're going to take the mass and velocity of each of these. So you take the because momentum, you know, is mass times velocity. So the momentum, the mass, 1875, times the velocity, 25. The momentum of the small is 1025, times its velocity of 17. Afterwards, the mass is the combined mass of both of them, 1825 plus 1025. So that's going to be 2900 times the velocity. And I got 2900 by adding 1875 to 1025. So then you just plug this in on your calculator to figure out the velocity that they move off together at. So 1875 times 25 plus 1025 times 17. I'm going to divide it by 2900. And I get 22.1 or 22 meters per second. So if something collides with one another and they stick together, it's pretty easy to find their momentums. Here's another kind of example of that. Now, when we have collisions, there's actually two different types of collisions. There's collisions where you stick together, and those are called inelastic collisions. The definition is kinetic energy is not conserved. They squish, if you will. Like throwing a medicine ball into something. An elastic collision is where kinetic energy is conserved. These would be a bounce. Now, no collisions are perfectly elastic, as are none of them are perfectly inelastic. You can never impart total kinetic energy. There's always something lost to heat or sound or something. But there was an interesting material that came out a few years ago that I'll let this guy explain.
Here's an astonishing bit of physics, fairly recently discovered. We've got two plastic tubes with lumps of metal in the bottom of them and little ball bearings. And when you drop one of the ball bearings in, it performs a bit like that. Nothing very exciting happens. However, this one here has got a layer of some exotic chemical they call it an atomic trampoline. You'll see why in a moment. But it's a liquid metal, amorphous structure, with nickel, titanium, zirconium, beryllium, copper in it. And unlike this one, it doesn't convert the impact, the energy of the impact, into heat energy, which this one does, or hardly any of it, so that it throws the ball up.
So in the first one, all the energy was lost to heat. Like as the ball would squish, it loses its energy into heat and sound. In this one, there's very little flexing of the material to lose it through heat.
Amazing. And quite a bit.
The second type is a separation. Like what if you've got, it says an astronaut is at rest in space and they fire a thruster pistol that expels 35 grams of hot gas. At this speed, the combined mass of the astronaut and pistol is this. How fast and in what direction do they move after firing the pistol? And this is actually a real thing that they do up on the space station. They have
shuttle kept a keen eye.
It's called the MMU, I forget what it stands for. It's something mobility unit.
Everyone had thought
Manned
out
mobility
emergency
unit.
scenarios, so we were keeping our radar trained on him, and our noses were up to the window watching. Bruce McCandless went out, flying out with this Buck Rogers type backpack 100 meters out from the spacecraft.
McCandless floated alone in space almost 6 hours and captured imaginations back on Earth.
The picture's iconic because it shows a human floating in space, right? I mean, if you think about it, he's really in his own little spaceship.
It's one of the coolest pictures ever taken. This guy
The
floating up above
experimental
the Earth all by
MMU
himself.
evolved into a much smaller device, now built into every NASA spacesuit.
Yeah, that smaller device they talk about, it's called the SAFER device. I actually got to see it and talk to the engineers down at the Johnson Space Center last year about that SAFER device. So here's one. You've got an astronaut at rest in space. He fires hot gas out. So here's before. And then after, you got your astronaut. You're expelling your hot gas this way, which will make your astronaut move that way. So the mass and velocity before are going to equal the mass and velocity afterwards. So, and it's really easy before, in this case, the mass, you could add them all up, but their velocities are 0. So the momentum in the before case is going to be equal to 0. And so what we're going to do, I'm going to have to define one of these directions as positive. So maybe I'll make to the right positive. So the mass of the gas, they say, is 35 grams. So 0.035 kilograms times the velocity. Well, what I'm going to actually do here is I'm going to take both of those. It's the momentum of the gas plus the momentum of the person. And that's going to be equal to 0 because it's, so the mass of the gas, again, 0.035, times the velocity of it. I think it was a big number, like 875. Now I'm going to make that negative because I defined to the right to be that. 0. And then my person, I know that my mass of everything together is 84. And with what speed does he move out afterwards? So this is kind of a simple little math problem to do. We're going to take 0.035 times 875. And then we move it to the other side, which makes it negative, and then divide by 84. And I get 0.36. So my velocity of my astronaut is 0.36 meters per second. So this is how we handle all momentum exchanges. Anytime we've got a collision or a separation, the momentum before is going to equal the momentum afterwards. So you look at the situation before, masses and velocities of all things before is going to equal the masses and velocities of all things afterwards. They could stick together, they could bounce off one another, but the momentum is conserved only if there's no outside forces or there's no mass lost or gained.